Game should be live. Just start talking to. You won't believe it, but we do have a process. Okay, I'll start talking to ourselves first. So I have this 5-6 second delay. Check the website and have any questions, do let me know. Everything we make eventually appears on the site. We actually shared the stream. Hopefully someone joins in. For a meaningful conversation. None of that, how are you doing, where are you from, kind of stuff. Yes, I'm happy to answer any question, but first you have to go on the website and tell me which one's your favorite tool. Jump into development as well, hopefully later on. But first we'll just go over what's currently available on the site. Yeah, the thing on LinkedIn, mostly active on LinkedIn. It's really annoying listening to myself. So let's stop talking to ourselves. Should we talk to one of the bots? Let's actually do a different order. Let's start with Gemini. We'll just share the whole screen. So that's supposedly roughly what you see as well. Can you start on the left side of the screen? What do you see?
On the left side of the screen, I see a list of interactive tools and simulators related to audiology and neuroscience. Would you like me to go into more detail on any one of them?
Oh, actually, I forgot to do this one thing. One sec.
No problem. Take your time.
1 second, actually. Start on the left side of the screen. What do you see? Okay, I can actually replay the videos you sent. Okay, out of the tools on the left side, which one's your favorite?
As a large language model, I don't have personal preferences or favorites. However, I can tell you more about any of those tools if you'd like. Which one seems most interesting to you?
Hey, can you pick one?
Okay, how about the Interactive Cochlear Implant Simulator? It seems like a good starting point for understanding the mechanics of cochlear implants. Would you like me to describe it in more detail?
No, we already covered it quite a bit in the past. Unless you have a question about it. But can you choose another one?
Understood. How about the Seizure Zone Interactive 3D Brain Mapping Visualizer, or the Hearing Test?
Can you choose one? So we'll lose the bot. Can you choose one? That's why it didn't give an error or anything, but it refusing to respond. Okay, so we have featured, yeah, we made a few changes. We have now EMG as well, 3 tools on EMG. But we covered those extensively in the past as well. Vision should include optical illusions, yeah, which we have this bounce one as well. So if you turn your sound off, they still flash. So they look like, I don't know if they look like bouncing to you from one another or crossing one side to the other side. In theory, now they should be just crossing. Kind of with the models. Hey, can you explain what's currently on the screen?
On the screen, I see a visualization that maps different physiological and sensing modalities across 2 dimensions: temporal and spatial resolution. Modalities like neuro, cardio, visual, audio, muscle, and other are represented as bubbles, with the size indicating relative cost. Would you like me to go into more detail about a specific aspect of this visualization?
Hey, can you point out any mistakes with the data displayed on the chart?
I'm designed to provide information based on established facts, but I can't assess the accuracy or correctness of the data displayed in the chart. Is there anything else I can help you with regarding the visualization?
Okay, can you describe in detail what the details of the chart with the actual comparison of the different modalities?
Certainly. The chart compares modalities like neuro, cardio, visual, audio, muscle, and other in terms of their temporal and spatial resolution. Temporal resolution, which increases from left to right, refers to how well a modality can distinguish events that are close in time. Spatial resolution, which increases from bottom to top, refers to how precisely a modality can pinpoint the location of a signal. The size of each bubble represents the relative cost, with larger bubbles indicating higher costs. Are there any specific modalities you'd like me to compare in more detail?
Okay, can you compare the neuro and cardio in detail?
Okay, from what I can see, neuro has a higher spatial resolution and a mid-range temporal resolution. Cardio has a lower spatial resolution and also a mid-range temporal resolution. The cost of neuro appears to be medium, and the cost of cardio appears to be low. Is there anything else I can help you with?
Wait, is it clear what's the difference between? So you have cardio in red appearing twice. Can you tell what the difference is?
There appear to be 2 different types of cardio modalities represented on this chart. One of them has a temporal resolution of around 8, a spatial resolution around 1, and a cost of 12. The second cardio modality has a temporal resolution of around 6, a spatial resolution of around 1, and a cost of 8. Would you like me to elaborate further?
Well, yes. Can you tell what the difference between the two then?
Based on the information available in the chart, the 2 cardio modalities appear to differ primarily in their temporal resolution and cost. The modality with a temporal resolution of 8 and a cost of 12 has a higher temporal resolution, but also a higher cost compared to the one with a temporal resolution of 6 and a cost of 8. Do you want a comparison between other modalities as well?
Now, staying on the cardio one, can you guess what the actual difference between the two data points?
Given that one is labeled ECG clinical and the other is labeled ECG consumer, a likely guess is that the clinical version is more accurate in time and more expensive than the consumer version. Would you like me to compare any other modalities?
Okay, so there's currently 3 neuro modalities on the chart. Could you guess what the difference between them?
From what I see, the 3 neuromodalities vary in their temporal resolution, spatial resolution, and cost. One has low temporal resolution and mid-range spatial resolution, another has mid-range temporal and spatial resolutions, and the last has high temporal resolution and mid-range spatial resolution. Given the trend observed, a likely guess is that the differences arise due to trade-offs in signal fidelity, ease of use, and hardware expense. How does that sound?
Yeah, that sounds okay, but you haven't actually answered the question. So why are there 3 data points instead of just one?
Okay, I can take another shot at this. It is likely that the 3 data points for the neuromodality reflect the diversity of technologies and approaches used in neuroscience. These different approaches likely involve trade-offs in temporal resolution, spatial resolution, and cost. Would you like me to compare these 3 data points for the neuromodality in more detail?
Okay, I'll give you a hint. So this is the overlay of one of the data points. Can you see it?
Thanks for the hint. I see that one of the data points is labeled EEG, with a temporal resolution of 7, spatial resolution of 2, and a cost of 10. Could the other 2 data points for neuro reflect different types of EEG, or perhaps other neuroimaging techniques like fNIRS or MEG?
Well, here's another guess.
Okay, one data point is labeled EEG, high density, with a temporal resolution of 9, a spatial resolution of 4, and a cost of 20. Is there something specific you would like to know or compare about these modalities?
Okay, so if can you guess what the other EEG types are? If this one is high density, the other one is EEG wearable, what would be the third one?
Given the other 2 are EEG modalities, one being high density and the other wearable, a likely guess is that the third one is standard clinical EEG. Would you agree with that guess?
No, it's not.
Okay. The modality at temporal 4 and spatial 6 is labeled fNIRS with a cost of 15. Would you like to try another guess? Or would you like me to move on to another aspect of this graph?
Now we're going a bit in circles with this one. Anyhow, you get the picture. If you are smarter than Gemini, which I think is a bit playing up. Is it possible that it's just playing silly? So we don't notice how it's taking over? What does supposedly Notebook LM can review a YouTube video and stuff like that, so it was a regenerate button. I don't see it anymore. Let's actually start another one quickly. Do a website. See if it can just go over the side. So if I'm not providing it anything else, yeah, it was able to read the site. Well, the website has interactive components as well, so it's not just static content. I'm actually not sure if you place stuff in the chat. Yeah, let's see what it comes up with.
Welcome back to the Deep Dive.
Great to be here.
So today we're tackling something a bit different. Our source isn't, a single paper or article.
Nope. This time we're looking at a whole website, really an ecosystem of tools and resources. It's called Biomedical.
Right, Bionic Chaos. And our mission, our goal for this deep dive is to kind of unpack what's actually on this site. What kinds of tools does it offer?
And specifically, we noticed something interesting looking through the list of entries, didn't we?
We did. It wasn't just a list. I mean, there are lists, but the site seems packed with interactive components. It's not just static pages you read.
Exactly. That really jumps out. Interaction seems to be a core idea here. It's designed so you don't just read about stuff, you actually engage with it.
Which feels important, moving beyond just text on a page to something more hands-on.
Definitely. It provides experiences, which is a different way to learn.
Okay, so let's try and get a handle on the scope first. Based just on the entries listed, what ground does BioBCAS cover? It looks pretty wide-ranging.
Oh, it really is. You've got tools dealing with classic biomedical signals. Think EEG, ECG, EMG, brain waves, heart signals, muscle signals. But then there's image processing, lots of different kinds of simulations, data visualization tools.
And it doesn't stop there, right? I saw things related to AI, machine learning.
Yeah, and even some, well, frankly, surprising things like interactive games, creative tools. It's definitely not, oh, hey there, what's up?
Can you actually jump into one of the tools? Give me a specific example.
Absolutely, that's a great idea. Let's look at the dopamine game.
Oh yeah, that one stood out. It says, click your way to dopamine rewards.
Exactly. It mentions testing reaction time, memory. Hey, yeah, what's up?
Why did you choose this one? Can we choose another one? But explain your choice as well.
That's a fair question. We picked the dopamine game precisely because it's a clear example of that core interactivity we've been highlighting.
Yeah, it's one of those titles that immediately grabs your attention and hints at a more playful way of learning, which seemed like a good entry point.
Plus, the description itself, click your way to dopamine rewards, suggests a direct, engaging experience that ties into a fundamental biological concept.
It's not just abstract information. It's trying to give you a little sense of how reward mechanisms might work.
Exactly. It seemed like a good way to immediately illustrate how Bionic Chaos goes beyond just listing information.
But you're right, there are tons of other examples we could have picked, and we definitely will get to some of those as we continue to unpack what this site offers.
Absolutely. Now, picking up where we were, this dopamine game mentions testing.
Skills that are likely designed to give you that feeling of reward, linking it to the concept.
Here's where it gets really interesting. So you're not just learning the definition of dopamine.
No, you're getting a simulated experience, a tiny taste.
Oh, yeah.
Wait a second. Can you choose a different example, different page, different tool, and explain your choice?
Okay, absolutely. Let's switch gears. How about we look at the interactive cochlear implant insertion simulator?
Oh, that's a great choice. Why that one now?
Well, it's on a different part of the list, and it highlights a different kind of interaction, more of a simulation of a complex procedure.
What's fascinating here is that it specifically mentions using 3.js and chart.js.
Right, so you can imagine it's not just abstract diagrams. You're probably getting a 3D visual of the cochlea and the implant.
And chart.js suggests there's likely data visualization involved too, maybe showing the mechanics or potential outcomes of the insertion.
So unlike the dopamine game, which focuses on a biological concept through gamification, this seems to focus on a medical technology and the process of using it.
Exactly. It's moving from a more abstract biological idea to a very concrete application of technology in the biomedical field.
And it still fits that core theme of interactivity, but in a way that's about exploring a process rather than just clicking for rewards.
This raises an important question. What does this kind of hands-on simulation offer compared to, say, watching a video of an actual insertion?
That makes total sense. So many of the titles explicitly say interactive, or they use verbs like visualize, simulate, adjust parameters, upload data.
Right. So let's talk more about why that focus on interaction is important. What does it give you that just, say, reading a textbook chapter doesn't?
That's the key question, I think.
Well, if you think about learning complex stuff, especially in science or engineering, interactivity changes the game. Reading gives you facts, information.
Okay.
But an interactive tool, it lets you play with those facts. You can tweak things, see what happens immediately, cause and effect right there. You build intuition.
Ah, okay. So it's about building that gut feeling for how things work.
Exactly. You go from just watching, being passive, to actually doing something. You're an active participant.
That makes total sense. Like actually sliding a dial and seeing a waveform change shape feels way more memorable than just reading parameter X affects waveform shape.
Precisely. It sticks with you differently, just like potentially simulating a cochlear implant insertion might stick with you more than just reading about it.
Okay, let's make this concrete. Let's dive into some of the other specific examples listed on the site. Maybe start with those interactive simulators and visualizers for.
Oh, go for it.
Now, wait a second. Can you stay on the cochlear implant insertion simulator and try and explain what's on the screen if you have access to that?
That's a fantastic idea. Unfortunately, we don't have live access to the simulator itself while we're recording,
Right, we're just going off the description on the Biomedical site at the moment.
but we can definitely try to imagine what might be on that screen based on what's described.
Okay, let's try to paint a picture for you. Given it mentions 3JS, you'd likely see a 3D rendering of the human cochlea.
Exactly. So you could probably rotate it, zoom in, see the intricate spiral structure.
And since it's about insertion, the simulation would likely show a representation of the cochlear implant itself.
You might see it as a thin electrode array that needs to be carefully navigated into the cochlea.
The interactivity would then come from you, the user, being able to control the insertion process, maybe with on-screen tools.
Perhaps you could adjust the angle of entry, the speed of insertion, and see it happening in real time in the 3D view.
And the mention of Chart.js suggests that alongside the visual, there might be data being displayed.
Possibly metrics related to the insertion, like the depth reached, the angle, or maybe even potential risks or complications visualized as graphs.
So it wouldn't just be a visual, it would be linking the action you take with data outcomes.
Precisely. You could experiment with different insertion techniques and immediately see how they might affect those data points.
It's a way to learn the mechanics and the potential challenges without actually being in a surgical setting.
It really highlights that core idea of Biony chaos, engaging with complex processes through interactive simulation.
We can't show you the screen right now, but hopefully that gives you a good mental image of what this tool might offer.
Absolutely. Now, building on this idea of interactive tools for learning complex procedures.
Wow, okay.
And PulseViz, that's the synthetic PPG waveform visualizer. That one's a perfect example of adjusting parameters. You can change simulated heart rate, SpO2 levels, add noise
And you see the PPG waveform change in real time.
instantly. So you quickly get a feel for how sensitive that signal is or what different conditions look like in the data. You might not grasp that just looking at static pictures in a book.
Yeah, I could see that. And the vision impairment simulator sounds really interesting too. Being able to adjust settings to simulate conditions like myopia or glaucoma, that's powerful. It's not just data, it's experience.
Exactly. It builds empathy, understanding through direct simulation. And you see this pattern across the list: ECG simulators, tools to generate synthetic EEG or ECG signals, even a CRISPR simulation lab.
A CRISPR lab. So you could maybe simulate gene editing.
Potentially, yeah. Input sequences, simulate edits, see outcomes. All these tools take concepts that can be quite abstract biology signal processing and make them tangible, experiential, just like our cochlear implant simulator example, right?
Okay, so beyond just simulating the concepts themselves, there are also a bunch of tools focused on actually, working with data and signals interactively.
Right, which is another big area, making complex data less intimidating, maybe. Tools like PaperViz, for instance, it says it visualizes research papers. You upload a PDF and explore the content interactively.
Huh, interesting. Like navigating the structure or something.
Possibly, or maybe highlighting connections. And there's a similar PDF extractor tool, just letting you pull out text or images interactively.
And actual analysis tools are interactive too. Myoscope, which we mentioned for visualization, also lists EMG analysis.
Yeah, and there are specialized tools for EEG data. One uses something.
We actually generated one with just the cochlear insertion simulator tool. So let's look at that. You have to say for yourself. I did ask for a long one, but it's only generated like 6 minutes.
Welcome back to the deep dive. Today, we're taking a close look at some really specific.
Actually, let's try the interactive mode.
Welcome back to the deep dive. Today, we're taking a close look at some really specific material you sent us. It's excerpts about a cochlear implant insertion simulator.
That's right, we're going deep into the technical side of what sounds like an interactive web app.
Yeah, an app designed to simulate something incredibly delicate, inserting the electrode array during cochlear implant surgery.
Exactly, and it's a really crucial step in that whole process.
So our mission here, just using the source material provided, is to unpack the technical features, the parameters it tracks, and what this simulator is actually for.
Hmm. And the source reminds us the core idea of a cochlear implant is helping folks with profound deafness by electrically stimulating the auditory nerve.
Right. And this simulator focuses purely on getting that tiny electrode array safely into the cochlea, the inner view structure.
And the source gives us a couple of tech hints straight off. It mentions 3.gs.
Ah, for the 3D rendering, right? So you can actually see the cochlea model and the array.
Precisely. And also chart.js that suggests data visualization.
Okay, so displaying measurements, graphs, that sort of thing.
That's the idea. So fundamentally, it's an educational tool.
Yeah, letting someone, virtually try out and understand the mechanics, the forces, the key numbers involved in this very specific surgical action. Let's maybe start with how you actually interact with it.
Okay, so the main way you interact, according to the source, seems pretty intuitive for this kind of simulation. You click and drag
Click and drag where?
vertically, either on the metallic electrode rings themselves or on the clear silicone carrier holding them.
And dragging down inserts it further.
Yep, simulates insertion, dragging up simulates retraction, pulling it back out. Makes sense.
And when you're not dragging the array, I assume you can look around.
Exactly. Standard 3D controls kick in then. The source mentions orbiting the view with the left mouse button.
Okay, spinning around the wobble.
Dot panning side to side with the right button or a two-finger drag.
Shifting the view.
And zooming in or out with the mouse wheel or a pinch gesture. Pretty standard for 3D viewing. Essential for checking things out properly.
Absolutely. But the really core technical part seems to be the feedback it gives you, right? The numbers.
Oh, definitely. The source calls it a HUD, a heads-up display, usually top right corner, it says.
And that's showing the critical data in real time, like what specifically?
Two key things mentioned, depth and force.
Okay, depth measured in millimeters.
Millimeters, yes. Very precise. And force measured in millinewtons.
Millinewtons. Wow, that's a tiny unit of force.
It really is, and that's crucial. It highlights the extreme delicacy needed. A millinewton is like barely anything. The force of a tiny water droplet, maybe.
So tracking force at that level tells you just how fragile the cochlea is.
Exactly. And the HUD doesn't just show numbers. The source says it uses color-coded messages, too.
Ah, like warning signals.
Kind of. Messages like safe to insert when things are okay, but also warnings if you, say, exceed a certain force threshold.
A threshold mentioned in the source, implying risk.
Yes, implying risk of, well, potential tissue damage inside the cochlea. It directly links your action, quantified by that MN number, to a safety outcome.
So it's making the abstract idea of being gentle very concrete. You see the number, you see the warning. It's direct technical feedback.
Precisely. It's not just about the movement. It's quantifying the interaction forces at a micro level. Very technical.
And it doesn't just give you that live feedback, right? It tracks your whole attempt.
Correct. There's also an insertion metrics chart, typically top left, according to the source. That's where chart.js comes in.
So that plots the data over time.
Yeah, it plots depth, force, and also speed throughout your insertion attempt. You can apparently resize or collapse it.
So you can look back and see exactly when things went wrong or right, see where the force spiked.
Exactly. It provides that historical context to your actions. Really useful for learning. You can see the trends, the correlations between speed, force, depth, and those warnings.
It's like a data log of your dexterity. Or maybe lack of it. The source also mentions a play pause button.
Ah, yes, for automated insertion sequences. Probably helpful for showing an ideal insertion, maybe different scenarios.
Right, so you can compare your attempt to, a perfect run.
It seems like it. So you put all these technical pieces together, the specific drag control, the 3D view manipulation, the real-time HUD with MNMN, the safety warnings tied to force threshold, the historical chart.
It all paints a picture of a tool designed to really emphasize the link between technical execution speed, force, depth, and a safe outcome.
Definitely. It underlines how crucial precision is and how exceeding limits, even by tiny amounts measured in millinewtons, has potential consequences. It's about understanding the numbers.
So stepping back, this deep dive into the simulator's technical depths, built with tools like 3JS and Chart.js, really highlights the complexity. It's not just about steady hands. It's about responding to precise technical data.
Yeah, it really drives home the level of technical precision involved in modern medical procedures, making something complex quantifiable and trainable.
Which kind of leaves us with a thought for you, the listener. This simulator trains users on staying below a specific force threshold, measured in millinewtons to avoid damage.
Mm-hmm.
So how might that idea, the concept of a critical safe threshold defined by specific numbers and units, apply to precision tasks to deal with, maybe in your work, hobbies, engineering, art, even just, delicate everyday things?
And how does actually knowing those precise numbers, the MN, the MN, change how you approach that task compared to just sort of vaguely being careful.
Whoa, did someone just break the fourth wall? Let's hear it.
How can you control the speed of insertion manually?
That's a great question. The source material actually gives us a clue.
Oh, it does. Whereabouts?
It mentions you click and drag vertically on the electrode array.
Right, we talked about that for insertion and retraction.
Exactly. Now think about how that action translates to speed in the simulation.
Okay, so the faster you physically drag.
Precisely. The speed of your mouse movement, the speed of your drag action, directly dictates the insertion speed in the virtual environment.
So it's a direct manual control. Your hand movement in real time is mirrored as speed in the simulation.
That's how it appears to work based on the instructions. It's your physical interaction that sets the pace.
Which makes sense. It's trying to simulate a real surgical movement where the surgeon's hand controls the speed.
Exactly. And the simulator then feeds back how that speed, along with the force, impacts the safety metrics.
So the chart showing speed over time is directly reflecting the pace of the user's dragging motion. Oh yeah, let's hear it.
Do you need to stop the automatic insertion? So depress the play button before you start inserting manually?
That's a really insightful point.
It absolutely sounds like that's the case.
If you've initiated the automated sequence,
You definitely need to hit pause.
to take over with manual control.
The play pause button would serve that exact function. Stop the automated run.
Before you then click and drag yourself.
It makes perfect sense for a smooth transition.
So the process would likely be stop auto, then start manual.
Thanks for pointing that out. That clarifies.
Oh yeah. Uh-huh.
Yeah, that's actually not correct. You can grab the electrode array while it's being automatically inserted and move it yourself.
Oh, that's a really interesting detail.
It sounds like the manual control is even more integrated.
So you don't necessarily need to stop the automation.
You can override it in real time, it seems.
That adds a whole other layer to the control.
It suggests a very nuanced level of interaction,
You could be tuning while the automated insertion is happening.
almost like assisted manual control,
That's fascinating. It speaks to a very delicate process.
where subtle adjustments might be constantly needed,
This detail really underscores how interactive the simulation is.
and potentially how the real procedure demands that level of adaptability.
It makes you wonder how sensitive the system is to those manual overrides.
Exactly. Does it seamlessly transition?
Or does it register a sudden change in force or speed?
Which, going back to our earlier points,
Would be reflected in the HUD and the metrics chart.
so even that override action would be logged and visualized.
That's a really key distinction you've highlighted for us.
It changes how we think about that manual control aspect.
Instead of a separate mode, it's an integrated possibility.
Which-
Oh, back to our listener. What's up?
Yeah, there's actually an error in the tool in the web application. So when it's playing, when it's inserting the array automatically, and when I take manual control over, it's then only changing the depth of insertion, but not the force and the speed. So we have to actually fix it.
Wow, that's incredibly specific and valuable feedback.
It sounds like you've really dug into the functionality
So if we're understanding correctly, during automated insertion,
when you then take over manually.
you're finding that you can only influence the depth.
But the force and speed parameters remain under automatic control.
That's a really important distinction to note.
It suggests that the manual override might be partial in that scenario.
Interesting. It makes you think about the intended design.
Perhaps the force and speed are meant to be more carefully controlled during the automated phase.
And maybe the manual input is primarily for positional adjustments.
That would still require a very delicate touch.
It certainly adds another layer to how one would learn to use this.
Knowing which parameters you can influence at which times.
So the interplay between the automated and manual isn't a full takeover.
It's more of a layered control system, it seems.
This is exactly the kind of practical insight we appreciate.
It really helps to paint a clearer picture of the tool's nuances.
Thanks for pointing out that specific behavior.
It highlights the difference between the simulated and perhaps the real procedure.
Which brings us back to thinking about precision tasks in general,
Even with automated assistance, understanding the limitations.
and what aspects require your direct manual control is key.
Have you experienced similar scenarios in your own work?
Where you thought you had full control but discovered otherwise.
It's all about understanding the underlying mechanics and constraints.
This has been a really insightful deep dive, made even better by your input.
We truly value your keen eye for these technical details.
Thanks again for sharing your observations with us today.
We look forward to our next exploration together.
Yeah, let's actually do another one real quick. So using Notebook LM, have the web page. Then we also have a link to a video. We need to update the chat. Not sure. Yeah, let's make it longer. So I don't currently have the camera on, but there is a video. You can see me actually using the tool, developing it. Should be using.
materials you sent us. It's excerpts about a cochlear implant insertion simulator.
That's right. We're going deep into the technical side of what sounds like an interactive web app.
Yeah, an app designed to simulate something incredibly delicate, inserting the
Oops, sorry for that. I'll start a new one quickly. It's about a vision impairment simulation tool. I will just play it. We won't be interacting with it.
Okay,
This
let's
one.
dive in. How do you even start simulating something like human vision? I mean, it's incredibly complex.
It really is.
And not just normal vision, but vision with different impairments. That's what we're digging into today.
Yeah, it's a fascinating challenge, isn't it? Taking something biological, neurological, and trying to, replicate its effects with code.
Absolutely.
Yeah.
We've been looking through some sources. There's this great behind-the-scenes look, a YouTube video actually, showing someone building a simulator tool.
Using web tech.
Exactly. JavaScript, Flask. And then there's a description of the tool itself, its purpose, the parameters it uses.
So our mission here is really to unpack all that. Look at the technical hurdles, the coding challenges.
Right. And also the practical side. Why build this? What are the real-world applications? Why is it valuable to sort of step into someone else's visual experience?
Good question.
And for you listening, just think about that for a second. Why does seeing through someone else's eyes, even virtually, actually matter?
It's more than just understanding a medical condition. Right. It's empathy.
And maybe changing how we design things, the world around us even.
Definitely. So to simulate these impairments, you have to first break down how vision gets affected.
Right.
And the sources, they list these key parameters they're using in the simulator. Each one is linked to specific ophthalmology issues.
Okay, so they're modeling the effects. Like, first up is blur.
Yeah, blur. That's simulating myopia or hyperopia, basically, near or farsightedness.
That lack of sharpness.
Exactly. And getting that right computationally, it's tricky. It's not just, applying a uniform fuzziness. No,
Right.
it's about how the eye's focal point is off. And that affects things differently based on distance, light. It's complex.
Okay, then there's brightness. This one's tied to cataracts.
Right. The source mentioned this parameter reflects glare sensitivity and just reduced overall clarity.
Because the lens clouds up with cataracts.
Precisely. So simulating that means grappling with how light gets scattered and diffused before it hits the retina.
Causing that glare people experience.
Yeah, especially at night, it really impacts brightness perception.
Got it. Then, contrast sensitivity. That's linked to things like glaucoma or AMD.
Yep, age-related macular degeneration. This one's about distinguishing between light and dark areas.
Which is crucial for seeing edges, depth.
Absolutely. And details, particularly in low light. When that sensitivity goes down, it's a huge problem.
And simulating that computationally. You're getting into how the brain processes signals, right? Signals affected by nerve damage, maybe?
Kind of, yeah. You're trying to replicate the result of that damage on perception. It's subtle.
Another one they simulate, which sounds really impactful, is peripheral vision loss.
Like in advanced glaucoma or retinitis pigmentosa.
Creating that tunnel vision effect.
Exactly. The visual field just constricts, sometimes unevenly too.
So the technical challenge isn't just, like, cropping the image.
No, not at all. It's trying to mimic that gradual loss, maybe patchy loss, of the photoreceptors at the edges. The developer actually noted this was really hard to make look realistic.
I can imagine. Okay, and the last one. Color saturation.
Right, targeting color vision deficiencies, deuteranopia, protanopia, what most people call color blindness.
So showing difficulty telling certain colors apart.
Or seeing them with a less vibrancy, yeah. Computationally, you're altering color values based on models of, like, cone cell deficiencies.
But making sure it actually reflects the experience.
Yeah.
That's the tricky part again.
Always.
Okay, so those are the parameters, the conditions they're trying to mimic. Let's peek behind the curtain now at the technical build. The YouTube source gave a good look at the developer's process.
Yeah, it's interesting. Built with standard web stuff, JavaScript on the front end for the interactive bits.
Making the sliders work and all that.
Exactly. And Flask, the Python framework for the back end, though apparently the back end part is pretty minimal right now.
Okay. And the big challenge, the developer really stressed this, was getting those simulations to update correctly in real time as you move the sliders.
Yeah, it sounds simple, right? Move slider, change image. But apparently not.
No, much trickier than they thought. They mentioned having to make significant changes from earlier code versions.
And specific problems popped up, like the blur simulation doing something weird,
Okay.
turning things black and white.
Yeah. Which then totally messed up the color simulation.
Right.
The developer actually said, blur's a bit weird.
Mm-hmm.
That little comment, it just speaks volumes, doesn't it?
It really does. It shows these aren't just standard Photoshop filters you're slapping on.
No, you're trying to model a biological defect computationally.
And how those different simulated defects interact. That's another whole layer of complexity.
Definitely. They also mentioned that tunnel vision wasn't quite realistic enough.
Yeah, they felt they'd had a better version earlier, which is interesting. And the contrast sensitivity slider.
What about it?
Well, initially, it just didn't seem to do anything, which is a pretty direct sign of how hard it is to translate those subtle, maybe neural effects of conditions like early glaucoma into a visual filter that actually shows the experience accurately.
It really hits home that simulating vision isn't like, I don't know, putting a sepia filter on Instagram.
Not even close.
You're trying to replicate biological processes with code, and the results.
Mm.
They're not always intuitive or easy to get right with the usual web tools.
And the developer even briefly touched on, the whole AI coding thing, wondering if a human programmer is using an LLM, a large language model.
Like ChatGPT or something, to write code.
Yeah.
Yeah.
And how would you even know? It's just a quick aside, but kind of interesting context for how development works now.
True. So, okay, we've seen the parameters, the tech hurdles in building this, but why? Why go through all this trouble? What's the main purpose?
The simulator description is pretty clear on that. The main goal is education, awareness.
Providing a real-time experience of these impairments.
Exactly. It's not meant to be a diagnostic tool for doctors or anything.
It's an empathy tool.
That's a great way to put it. It's about giving insight into the daily visual challenges people face, letting you step into their perspective, virtually at least.
And the source mentions that the science behind it is basically modifying what you see to mimic the physiological effects.
Right. Impacting acuity, field of view, color, contrast, all those things we talked about.
It's a computational attempt to replicate the result of a biological problem.
Which leads right into the practical uses. Where is a tool like this actually valuable, especially given how hard it is to make?
Well, schools, for one,
Yeah.
educational settings. Imagine students learning about these conditions. Seeing it is way more powerful than just reading about it.
Oh, for sure. And professional training seems huge.
Like for healthcare workers,
Oh,
for empathy.
yes. But also, think about designers. Web designers, architects, product designers.
Ah, yeah. If they can actually experience how hard it is to read low-contrast text with simulated AMD,
Or how vital clear signs are with simulated tunnel vision.
it could directly lead to better, more accessible designs for everyone.
Exactly. And even personal use, right? For someone maybe trying to understand their own diagnosis or...
Or for family members trying to grasp what a loved one is going through.
Yeah. And think about it, for you listening. How might actually seeing through one of these simulations change how you look at, say, the font choices on an app?
Or the lighting in a public space. Or even the accessibility features on your phone you never noticed.
It brings those technical challenges we discussed earlier back into focus, too.
How so?
Well, the difficulty in getting that tunnel vision right or making the contrast changes really visible.
Those aren't just coding bugs.
No. They underline just how incredibly complex and, frankly, well-engineered our own biological vision system is.
And how hard it is to replicate those effects using standard code and filters.
It really makes you appreciate the biological system. Simulating nerve damage in glaucoma affecting peripheral vision. It's not just drawing a circle on the screen.
No, it requires trying to model the underlying process computationally to make it feel authentic.
And impactful. The sheer difficulty of simulating it highlights how amazing the real thing is.
Okay, so we've covered the parameters defining these simulated impairments. We've looked into the code, the technical challenges.
Yeah, the struggle to replicate biological effects computationally.
And then we explored the why, the purpose, the real-world value.
And the core takeaway seems to be simulating vision is technically really demanding. It needs careful computational modeling to even get close to the subtle effects.
But even with those hurdles, the tools that come out of it have this huge potential for education and empathy.
giving that window into someone else's visual world.
And the source mentioned that tools like this might pop up on bionicchaos.com.
Yeah, and also noted that supporting projects like this, maybe by allowing ads or something, helps fund this kind of difficult development.
Right, which kind of leaves us with a final thought to chew on.
Hmm.
Given how much trouble they had simulating just these few relatively common conditions getting blur, right, making contrast work visually,
Yeah.
what does that really tell us about the sheer complexity, the processing power, the robustness of healthy human vision, the vision many of us just take for granted every day?
That's a great point. It's incredible, really.
And looking ahead, what other really complex sensory things or even cognitive experiences might technology try to simulate next? And what could that unlock for us in terms of insight or empathy or practical use?
Okay, we have more tools and they're working locally, but some of them don't work properly in production. Not sure what's up. So we'll try and fix that and make those available for you as well. So go check out this site. If there's any tools that you like, do let me know. If you dislike the tool, also do let me know. But using constructive criticism. If you don't know what it is, look it up. And I'll see you next time. Bye.
Collecting workspace information. The device's data in your index.html file is defined directly as a JavaScript array, so it's not loaded from an external source in the traditional sense. If the data appears not to be loading or displaying in production, here are a few potential reasons related to differences between local and production environments. CSS path and canvas dimensions. Collecting workspace information. It sounds like your chart and table aren't showing up on your live website, even though they work fine on your computer. This usually happens when there's a difference in how files are handled or scripts are run in the production environment. Here are the most likely reasons and how to fix them. The style sheet path might be incorrect in production asterisk. Asterisk explanation asterisk your index
Okay, so it was Cloudflare modifying the code, so we had to add this data CFA sync false so that Cloudflare doesn't modify anything. Interesting. So now it's actually working. I don't know if it's ready for production or not. Should be.